In the previous lecture, we have started multiple regression models. In the multiple regression model, I have explained how to do a multiple regression model, what is the meaning of beta 0, beta 1, beta 2, and also I have explained what is R square and adjusted R square. In this lecture, we are going to see how to do the significance test. That means here also, like simple regression, we are going to have some hypothesis about beta 1 coefficient, beta 2 coefficient and so on. Then we are going to test whether the beta 1 is equal to 0 or not equal to 0. So, what we are going to do in this lecture is, we are going to test the significance of regression model with the help of Ftest and T-test, and I am going to do a Python demo for a multiple regression. Ftest is used to determine whether a significant relationship exists between the dependent variable and the set of independent variables. We will refer to the Ftest as the test of overall significance. I will show you where this Ftest is appearing in our Python output. If the Ftest shows an overall significance, the T-test is used to determine whether each of the individual independent variable is significant or not. A separate T-test is conducted for each of the independent variable in the model. So, we refer each of these T-test as a test of individual significance. So, Ftest is used for testing the overall model of regression equation. The T-test is used to test for individual independent variables whether they are significant or not. In the Ftest, what is a null hypothesis? Here null hypothesis is beta 1 equal to beta 2 up to beta p equal to 0. When I accept null hypothesis, what is the meaning is, for example, if I accept beta 1 equal to 0, there is no relation between x1 coefficient and the dependent variable y. If I accept beta 2 equal to 0, there is no relation between x2 and y variable. Obviously, alternate hypothesis is one or more of the parameter is not equal to 0. So, how to find out the F statistic? The F statistics is MSR divided by MSE, that is the mean regression sum of square divided by mean error sum of square. How we are getting this mean regression sum of square? When you divide SSR divided by corresponding degrees of freedom. Here the degrees of freedom is P divided by, then we will get MSR. For MSE, when you divide SSE divided by n minus p minus 1, where p is number of independent variable, then we will get the mean errors sum of square. This hypothesis testing can be done by two ways. One is by p value approach, another one is by critical value approach. In the p value approach, reject H naught if the p value is less than or equal to alpha. What will happen? This is Ftest, it will be this way, it is a right skewed data, this is your alpha value. Here you will get F alpha corresponding, this value you can get it from the table. So, what you have to do? You have to find out the p value. If the p value is lying on the rejection side, you have to reject it. Otherwise, if the f value is beyond the f alpha value, we have to reject it. Where f alpha is based on the f distribution with the p degrees of freedom in the numerator and n minus p minus 1 degrees of freedom in the denominator. So, we got f equal to 10.8 divided by 0.328 equal to 32.9. I will show you in the ANOVA table. You see that this f value, in the previous slide we are showing f value is 32 point. So, this value 32.88, that is a 32.9 approximately. Then we can see the, you see here the p value, probability of static, this value, p value is less than 0.05 when you say alpha equal to 5%. So, then also we have to reject our null hypothesis. So, this is ANOVA regression table. What are the sources of error? Error due to regression variable, error total, regression sum of square, error sum of square, total sum of square. Look at the degrees of freedom, that is more important. So, if there are one independent variable, the degrees of freedom is 1 for regression sum of square. For TSS, that is a total sum of square, for that n minus 1, n is number of data set. So, when you subtract n minus 1 minus p, that is why this we are getting n minus 1 minus p is n minus p minus 1. So, what is MSR? MSR is SSR divided by p, MSE is SSE divided by n minus p minus 1. So, F equal to MSR divided by MSE. This is the F value which we got in our ANOVA output. See, when we introduce both the variable into the model, corresponding ANOVA table for that two independent variable regression model is this one. So, this is an ANOVA table. First, we will find out regression sum of square, error sum of square SST. P is the degrees of freedom, P is the number of independent variable. For SST, the degrees of freedom is n minus 1. If we want to know the degrees of freedom for SSE, so n minus 1 minus p, that is n minus p minus 1. MSR equal to SSR divided by p, MSE equal to SSE divided by n minus p minus 1. Finally, we are getting F value. So, this F value is nothing but your 32.88. Now, we will go for individual. For each variable, we will see that significant whether that individual variable is significant or not. For any parameter beta I, H naught equal to beta I equal to 0, HA beta I not equal to 0. The test statistics is BI divided by SBI. Actually, this should be this way, BI minus beta I divided by SBI, because we are assuming beta I equal to 0. So, the remaining is only BI divided by SBI. This SBI for ith independent variable, we can see that is a standard error. When I go back, you see this. The standard error for x1 is this one, 0.010. The standard error for second independent variable is 0.0221. Okay. That value we can get it this one. So, for p value approach, reject H naught if the p value is less than or equal to alpha as usual. Critical value approach, reject H naught if the t value is below the lower tail or above the upper tail. Here the t alpha by 2 is based on the t distribution with n minus p minus 1 degrees of freedom. Okay. We will do that one. So, beta 1 is 0.0611. Where we got this one? I am going back. T test for individual significance. So, from our output of our Python model, we got B1 equal to 0.061135, B2 equal to 0.9234, SB1 equal to 0.009888, SB2 equal to 0.2211. Where we are getting, just see that B1. So, B1 is this value 0.0611. The SB1 is this 0.011. I am going back, see that SB1. So, 0.0098. So, it can be 0.01 because after rounding. Okay. The B2 is 0.92, see that B2 is 0.92, SB2 is 0.221. So, what is the T formula? B1 divided by SB1, B1 is 0.061135 divided by 0.088, 6.8, here T is 4.18. So, this also we can verify, where is a, for first variable it is 6.18, see that 6.18. For second variable this is 4.16. Look at the p value. P value for first variable is 0.000, second variable it is a 0.00. By looking at the p value itself, we have to reject our null hypothesis. When we reject null hypothesis, beta 1 not equal to 0, that means there is a relation between x1 and dependent variable y at the population level. Similarly, for the second independent variable also, we have to reject null hypothesis. So, beta 2 not equal to 0, that means that there is a relation between x2, that is the second variable, number of deliveries, and the dependent variable. This is the way to interpret the Python output of this multiple regression model. I am going to give you a demo for the multiple regression model. Okay student, we have seen the theory behind the multiple regression model. We have come to Python background. I have already prepared the code, I have shown the output. Suppose we want to do a demo in our class, or you want to explain to someone these codes, you go to this kernel, there is option restart and clear output. So, what you will get it, there is a restart and clear all outputs. When you do this way, you see that only the codes will be there won't be any output. Suppose if you want to show to others what is going to be the output of these codes, you can do that way. So, first we will import the necessary libraries. Import pandas as PD from statmodels.formula.api, import OLS. So, this library is used for doing regression analysis. As you know that the pandas is used for reading or loading the files. From statmodels.stat.ANOVA, import ANOVA _LM. So, this library is used to see the output of ANOVA table for a regression model. Import matplotlib.pyplot as a PLT. So, this is used for plotting the figures. First, I have stored my data set. The file name is called trekking. I have loaded this data set into the object called df1. First, we will run the library, then we will see what is the data set. In this data set, when you look at this, the first one is the index column, second one is the driving assignment, the third one is our independent variable, that is the travel time. The next one is number of deliveries, the third one is now the travel time, it is the distance travelled. The x1 means distance travelled, the next independent variable is number of deliveries, the travel time is our dependent variable. Here what we are going to do, first we are going to see what is the relation between x1 and our dependent variable, then we will see x2, that is our number of deliveries versus travel time, then we will see both independent variable together, then we will see what is the effect on the dependent variable. First we will do the scatter plot, then we can understand the relationship, the trend between each independent variable and the dependent variable. Yeah, this one is x1 is taken as the independent variable and y is taken as the dependent variable. It seems to be there is some positive trend is there. Why this scatter plot is required? If there is no relationship at all, suppose the lines are in a horizontal manner, that you need not do any regression analysis because there is no relation between this x and dependent variable. Now we will take a 2 variable, then we will plot it. Now what is happening? The green dot shows one variable, the red dot shows another variable. Okay. Now this is only the second independent variable. Now we will go to the regression model. The first regression model where we are going to consider only one independent variable. So that is model name is reg1 equal to OLS. The formula equal to travel underscore time is the dependent variable, tilde symbol. Actually the first we have to write the dependent variable tilde x1 in double quote, data equal to df1. Because this tilde symbol, even if you know the R programming, in R programming also similar syntax we will use that one. So when you do this one, we are getting the output of our regression model where only one independent variable is considered. So what is the first task is we have to construct the regression equation. What is the regression equation? Y equal to 1.2739 plus 0.0678 x1. Second one is we have to look at the R square. R square is 0.664. If the R square is more than 50, it is considerably is a good model. Even though it is 66, this is accepted. Then look at the F statistics. F statistics 15.81. Then look at the probability. Probability is less than 0.05. As a whole model, this regression model is acceptable. Remember that we are using only one independent variable. Then you look at the p value when for the first independent variable, it is a 0.004. It is less than 0.05. When you look at an individual variable also, this x1 variable is significant variable. The next one, what we are going to do, we are going to introduce both the independent variable together, then we are going to see the impact on R square. So here I am going to say that model is regression 2, reg 2 equal to OLS, formula equal to travel time, tilde x1 plus I am adding the second independent variable. If there is a third independent variable plus you have to add the third independent variable. Then fit2 equal to reg2 dot fit. So, print fit2 dot summary. Yeah, look at this. First we will come regression equation. Regression equation is y equal to minus 0.8687 plus 0.0611 x1 plus 0.9234 x2, otherwise number of deliveries. You compare the r square with the previously, see r square is 0.664. Now when you use two independent variables, the r square is increased. So the goodness of fit of the model is increased when we introduce more independent variable. There is another term adjusted r square. This is adjusted for number of independent variables. When you are keep on introducing more number of independent variables, we have to monitor the value of r square and adjusted r square. What will happen when you introduce more independent variables? R square will always increase, but adjusted r square, it will initially start increase, after a certain point it will start decreasing. That point you should stop adding more independent variable. That means if the r square value is decreasing, that the new variable which you have introduced into the model is not helping to explain the regression model. Instead of, it is going to disturb the existing model. That is, that new variable which you added is the noise variable. Look at the f value, f is 32.88. Look at the probability value, it is less than 0.05. As a whole model, so we have to reject null hypothesis. So what this f statistics says, the f statistics is used to test overall significance of the regression model, that both x1 x2, by considering in this regression equation, the model is valid. Then we will go for significance of each individual independent variable. There is x1, when you look at the p value, it is 0.000. That means we have to reject our null hypothesis of beta 1 equal to 0. When you reject it, that means beta 1 is not equal to 0. When you say beta 1 is not equal to 0, even at the population level there is a relation between x1 and the y variable. Similarly, look at the p value for the our second independent variable, that also less than 0.05. That means that the second variable also significant variable in our regression model. Sometime what will happen, there may be different independent variables. For some independent variables the p value will be more than 0.05. If it is more than 0.05, when you are writing regression model, that corresponding independent variable has to be dropped. So meaning of the dropping is that with the help of sample data we can write a regression equation by considering all independent variable, but that cannot be generalized at the population level, because certain variable may not be significant at the population level. How to know that the variable is not significant? You have to look at the p value. If the p value is more than 0.05, we have to accept null hypothesis. When we accept null hypothesis, that means beta 1 equal to 0, that means there is no relation between that independent variable and the population. Other goodness of it is there, we will see the what is the meaning of Durbin-Watson in the coming classes. Similarly, there is one more measure to check the goodness of model AIC and BIC. When you go for our logistic regression, then I will explain what is the meaning and significance of AIC. So far we have studied regression analysis. Now with the help of regression, I am going to tell you how to solve an ANOVA problem. I have taken one sample problem. That problem first I am going to solve with the help of ANOVA, then with the help of Excel I am going to solve it. After that, the same problem I am going to explain how to solve that ANOVA problem with the help of regression analysis. The problem is like this. What is happening? There are three columns is there, A, B and C. The A represents one type of assembly method, B represents another type of assembly methods, C represents the third type of assembly methods. If you follow method A, the 58, 64, 55, 66, 67 represents number of product which are assembled per week. Similarly for B, under the column B, 58, 69, 71, 64, 68 represents number of product assembled per week. Here the product is filtration system. As a manager, I wanted to know which method is producing the better result. That means, if I follow method A or B or C, which one will produce or will help me to assemble more number of products. This a typical an ANOVA problem. So, in ANOVA what we used to do, generally the null hypothesis is, I am writing here, the null hypothesis is mu A equal to mu B equal to mu C. That means, the mean of the product assembled through method A is equal to mean of the product assembled by method B equal to mean of the product assembled by method C. Obviously, the alternative hypothesis is mu A not equal to mu B not equal to mu C. The purpose of doing this ANOVA is to identify which assembly method is more productive. In case if I accept null hypothesis, all the 3 assembly methods are giving the same result, I am not able to identify which method is better. In case if I reject my null hypothesis, I can clearly say which method is the better method, which will give you a more number of product assembled. This I am going to solve with the help of Excel. I have entered the data in 3 columns, column A, column B and column C. So, go for data, go for data analysis, go for ANOVA. ANOVA it is a single factor because it is a one way ANOVA. So, the input range is, I am selecting all these values. So, labels in the first row, yes. So, when I say OK, I am getting this output. What this mean is, when I look at the p value here, it is 0.00382, that is less than 0.05. So, I will be rejecting my null hypothesis. When I reject null hypothesis, all the 3 assembly method not producing equal result. This was the output which I am got it. So, how to interpret this output? When you look at this p value, the p value is less than 0.05. So, I am rejecting my null hypothesis. Now, this result what I have got in the previous slide, I am going to get with the help of regression analysis. In the regression analysis, I am going to use the concept of dummy variable, because there are 3 assembly method is there. Generally 3 minus 1 number of dummy variable is required. How I am creating dummy variable? I am taking say A, this is A is one dummy variable, for example B is another dummy variable. If I say 1 0, that represents the presence of 1 represents variable A. If I say 0 1, the presence of 1 represents on column B represents the B variable. See that the absence of 1 on both the columns represents assembly method say, that is why it is written here. See the 1 0 observation is associated with assembly line method A, 0 1 represents the observation is associated with assembly method B, 0 0 represents the observation is associated with assembly method C. So, I am going to do this modification, then I am going to do a regression analysis. So, with the help of regression I am going to explain here, but after some time I am going to explain to you how to use Python. So, first now I will explain with the help of Excel. This is the given data set. So, what I have done, this is my after coding. For example, you see that up to 58 to 67, this column up to this much it represents A. So, I have written 1 0 1 0 1 0 1 0. See that here it is up to 1 0 1 0. The presence of 1 represents assembly method A. The absence of 1 represents assembly method B. Similarly, I have typed the remaining B values. See that here 0 1 0 1 0 1 0 1. So, this portions represents, look at this, the presence of 1 represents assembly method B. The last one is this portions. So, I have taken 0 0 on both the columns, that means absence of 1 on both the method represents the assembly method C. Now, this one I am going to do the regression analysis. Go for data analysis, go for regression. Here the y value is this one, x value is, here there are two dummy variable, right, this one, then when you run it you are getting this output. You see that when you look at the p value here, here also you are getting 0.00382, that means here also you are rejecting one null hypothesis. I will explain how to interpret the coefficient of 52, 10, 14 in coming slides. See, the expected value of y is equal to expected value of number of units produced per week. This is the regression equation, beta 0 plus beta 1a plus beta 2b. If you are interested in the expected value of the number of units assembled per week for an employee who uses method C, our procedure for assigning numerical value to the dummy variable would result in setting a equal to b equal to 0. Suppose if you want to know the answer for assembly method C, we have to substitute a equal to 0, b equal to 0. When you substitute a equal to 0, b equal to 0, so the expected value of y is nothing but your beta 0. In case for method A, the value of the dummy variable is a equal to 1, b equal to 0. So when you substitute in the regression equation, you are getting beta 0 plus beta 1, 1 because a value is 1, here b value is 0. So beta 0 plus beta 1. If you want to know the expected value of assembly method B, we have to set a equal to 0, b equal to 1. So when you substitute in the regression equation, you are getting beta 0 plus beta 2. Now what we got it, when you look at these coefficients, the intercept is 52, that is your beta 0. So this is beta 1 for coefficient of A, this beta 2 is coefficient of B. What will happen? See, beta 0 is 52, beta 1 equal to 10, b2 equal to 14. If you want to know the estimated value of y for assembly method A, you have to refer, see b0 plus b1, how we got b0, b1? Look at this, beta 0 plus beta 1, we know beta 0 is 52, b1 is 10, so total is 62. If you want to know the estimated value of y for assembly method B, it is 52 plus 14. How we got 52 plus 14? Using this equation, beta 0 is 52, beta 2 is 14. What is beta 2? Look at this, beta 2 is 14. So when you substitute here, we are getting 66. If you want to know the expected mean of method C, you have to substitute a equal to 0, b equal to 0, then you will get only beta 0. Beta 0 is estimated with the help of b0, that value is 52. Then we can go for significance test, beta 1 equal to beta 2 equal to 0. This we have seen already. We can go for t test or f test. In the f test, if the p value is less than 0.05, then we can say both the variables are significant. So what happened here, when you do with the help of Excel, you see that the p value of f, see the p value is less than 0.05, we can say the regression coefficient A and B is significant. So far I have done with the help of Excel. Now I am going to do the same problem with the help of Python. First we will import the necessary files like import pandas as pd, import statsmodels.api.sm, from statsmodel.formula.api import OLS, from scipy import stats, import statsmodel.formula.api as SMF. The data is stored in a file called chemitech, running this. So this is my data set. So for this data set, I am going to do an ANOVA. After doing ANOVA, I am going to check the result. The same problem I am going to run with the help of regression analysis. For doing the regression analysis, I am going to use the concept called dummy variable. So first I will run this given data set ANOVA. So for that purpose, I am converting this data set into this form. What is that form? That I will show you in the data underscore R. You see that all the treatments are in one column, all the values are in one column. Model equal to OLS, value is our dependent variable, tilde, see the treatment is my independent variable, the command for regression analysis. From the regression analysis, I am going to get the ANOVA table. So the ANOVA table is this one. You see that the p value is 0.0038. When I am doing the The same problem with the help of Excel also we got the same result. So what we are concluding here all the means are not equal, so we are rejecting our null hypothesis. Now for this problem we are going to do with the help of regression analysis by using the concept called dummy variables. There are one treatment, that is the assembly method, but there are 3 variables A, B, C. So that I am going to convert into dummy variables. You see, look at this, A, B, C, you see the presence of 1 represents A, the presence of 1 represents here represents B. See the C column, so the presence of 1 represents C, because in the treatment there are 3 levels, we need only 2 dummy variables. So we are going to drop the column C, then we are going to use the 2 column A and B. In the Excel also, when I am solving, you might have seen this kind of data. So what I am going to do, I am going to drop this column C, then I am going to add these dummy variables into the file name called step_1. So this one, see that now the file is changed now, so the value is taken as it is, see only the column A and B is maintained. So for this data set I am going to do the regression analysis. So the result equal to smf.yls step_1, the value is my dependent variable, comma sm.add_constant step_1, A comma B is my independent variable, then I am going to get the regression output. When you look at this regression output, look at this probability, that is a p value, here also it is 0.00382. So here also we are rejecting our null hypothesis. Then look at the constant value, constant is 52, that is B0, B1 is 10, B2 is 14. So this value is taken for interpreting the output. Now look at the variable A and B, both are, the p value is less than 0.05, both the variables are significant. The value of B0, B1, B2 can be used for interpreting, as I explained in my slide, for interpreting the output. In this class we have seen how to do the significance test for multiple regression model. That significance test we have done with the help of 2 tests, one is Ftest and T-test. Ftest is used to test the overall significance of the regression model. T-test is used to check the individual significance of each independent variable. After that I have taken a sample problem, then I have explained, I have given a demo how to do the multiple regression, then we have interpreted the output of multiple regression model. In the next class we are going to do another regression model, that is where the independent variable, that is categorical independent variable. So far what we have done, that one dependent variable and independent variable both are continuous. There may be a situation where that independent variable is categorical variable. For example, gender is a categorical variable that can have only 2 options, male or female. In that case we have to do some adjustment in the existing our regression model. How to do that one, that we will see in the next class. Thank you very much for listening.